Greetings of the day to all of you. Today we begin our lecture series on advanced power electronics for 7th semester BTech in electrical engineering at NIT Srinagar. I would like to believe that you are pretty well aware of the basics of power electronics that you have been acquainted with in the last semester. So I'm assured that you are well aware of the operation of devices, particularly fully controlled devices like IGBT, MOSFET, and the operation of different types of converters. In advanced power electronics, you are going to mostly study DC to DC converters and DC to AC converters with greater detail, particularly as compared to the last semester. And we'll also introduce some new concepts and interesting topics in power electronics, which are usually taught at some places at the postgraduate level. One of the most interesting courses that I have personally felt in my BTech during my BTech studies. I hope that I can make it as exciting for you. Before we begin, let me give you a brief overview of the syllabus. So you know that power electronics is the conversion of electrical power or its control through power semiconductor devices. So essentially, by the use of power devices like IGBTs, MOSFETs, or thyristors, power diodes, you bring about power conversion or power control in a very efficient manner through power electronics. Now, broadly, you can have 4 types of conversions: DC to DC, DC to AC, AC to AC, and DC to AC. Wherever you operate in the AC domain, that is whenever you want to generate an output AC, either from a fixed input AC or from a fixed input DC, you generally want control over voltage as well as control over frequency. And when you are operating in the DC domain at the output, you generally want to regulate just the voltage because frequency has no meaning as such. Now, you must be aware of some types of converters in each of these domains. In this semester, we are mostly going to focus in this course on DC to DC converters in depth, in greater detail, and a little bit on, not actually a little bit, but quite significantly on DC to AC converters, again in detail. Since my area of expertise lies in AC to AC converters, so I might introduce a little bit of AC to AC converters to you towards the end of this course, since that is not part of undergrad studies, this particular converter that we'll discuss. So it'll just be a brief introduction. I'm assuming that you have already studied AC to DC converters in great detail in the previous semester, so it will mostly not be part of this course, but maybe we may slightly discuss AC to DC converters in the form of PWM rectifiers towards the end if we find time. So I would like to begin this course with DC to DC converters for this simplicity, and because essentially DC to DC converters are the building blocks of almost all types of converters. So now DC to DC converters, you often call them choppers. They can be broadly classified as isolated DC to DC converters or non-isolated DC to DC converters. In the previous semester, you might have studied non-isolated DC to DC converters, the buck converter, and the boost converter, or maybe even the buck boost converter, which are non-isolated converters, which means that there is a common ground point between the load and the source, and there is no electrical isolation between the two sides. Isolated DC to DC converters, on the other hand, have electrical isolation in the form of a small pulse transformer. We have to study these also in this semester, as well as the non-isolated DC to DC converters in greater detail. And particularly isolated DC to DC converters are very popular in electrical power supplies, switch mode power supplies, because of the protection ability of protection that they imbibe into the converter. So let's begin with the non-isolated DC to DC converters, which are buck converter, boost converter. You have buck boost converter, and then there are other converters called Sepik, Chuk, even Zeta. So probably we'll try to study most of these in detail, and then we'll move on to isolated DC to DC converters, which has flyback converter, forward converter, and push-pull converter in your syllabus. So let's begin with non-isolated DC to DC converters without wasting much time. I have already discussed the books that you're going to refer. For DC to DC converters, the book by Erickson is one of the finest. If you want a PDF copy, please leave your email IDs in the WhatsApp group, class WhatsApp group. I can email that to you. I'll email that to you. Okay, moving on to DC to DC converters. Let's start with the simplest of DC to DC converters, that is the buck converter. I have already shared a lecture with you where I have discussed the basics of buck converter, but we'll study this converter in slightly more detail today. So you have an input voltage source, say let's call it VDC, and across the load you desire some output, which is a controlled version of the input, which is less than or equal to the output voltage VDC. To bring about this conversion, you use a fully controlled device. So you are essentially sampling the input and the output through this power electronics device. And as I have already explained in the previous lecture in the last semester, I have shared those links with you, that in order to control or take care of the inductive energy of the load or the filter that you use in this circuit, you also need a freewheeling path, which is provided by a freewheeling diode over here, which is a fast recovery diode. And you have L and C, which are not necessarily present in a buck converter circuit, but in power supply applications they will almost always be present to ensure a ripple free smooth output. So you have some inductance, some capacitance in the load on the load side in the form of an output filter, and you have some power electronics devices, a switch and a fast recovery diode. Now I'll begin with the basics so that we have some continuity. Let's see what happens with the circuit when we give pulses and we try to operate this converter. So let's assume that I have given some pulses to the switch S at any given duty ratio, say D. So for 0 to DTS, my switch is on, and then DTS to TS, my switch is off. So this is my entire interval TS, switching interval. Now when my switch is on, it is conducting. The power circuit looks like this. The switch is behaving like a short circuit. The freewheeling diode is reverse biased, so this part is open, and this is how the circuit is going to look like. So what happens is that due to the switch being on, the supply starts storing energy into the inductor and partly into the capacitor, and this energy also goes into the load. Now interestingly, this inductor is definitely storing energy in this interval, but it is not sure whether the capacitor is storing energy or it is releasing energy. That essentially depends upon the state of charge of this capacitor and the energy requirement of this load. We will discuss this later. You'll come to know whether the capacitor is storing energy or the capacitor is releasing energy. by means of the waveforms. So in this interval, which is also known as the energy storage interval in the context of the inductor, we know that the inductor voltage VL is equal to VDC minus V0, where we have defined VL like this, V0 like this, and VDC of course like this. It's already shown, VDC like this. So the voltage across the inductor from simple case KVL is VDC minus V0 in the interval 0 to dTs, which is the energy storage interval for the inductor. Now, because it is a buck converter, the output voltage of the converter is less than the input, and VL is naturally, it comes out to be positive, which means that L di by dt is positive. VL is equal to L di by dt is positive because V0 is less than VDC, and because it is positive, it means that di by dt is positive, or you can say that the current is increasing. The current through the inductor IL is increasing. Please do not confuse IL with load current. We have used the notation I0 or V0 for load parameters. The L here represents your inductor. So in the energy storage interval, that is 0 to dTs, when the switch is conducting, the inductor is storing energy. The capacitor might be storing or releasing energy depending upon its state of potential and the energy requirement of the load, and obviously the energy of associated with the inductor as well. And we also know that since the inductor is definitely storing energy, the voltage across this inductor is positive, and the current through this inductor is rising. The main device is conducting, but the diode here is not conducting and it is blocking some voltage. What is that voltage? Let's call it, the diode was connected like this, right? So let's call it VDF freewheeling. So VDF freewheeling diode, voltage across that diode is minus of VDC if you see the convention, the way you have connected the diode. So minus of VDC, it means that when you choose this diode, when you have to select this diode, you have to select it with a voltage rating equal to the input DC voltage. It will be stressed to a maximum negative voltage equal to the input voltage of the converter. So if you have an application where you have 100 volt input, you need at least 100 volt diode that can block minus 100 volts. Obviously it cannot block anything in the positive direction, but negative of 100 volts it should be able to block. Okay, so this was about the energy storage interval. Now the pulse is withdrawn at DTS, and let's see how the circuit looks like. So you have the same source, but the switch will not conduct anymore. The inductor is still in the circuit, the capacitor is still in the circuit, the load is still in the circuit. And you have a diode, which we do not know as of now what happens to the diode. So suddenly it looks like that you interrupted the current flowing through this inductor, which had been rising previously, and suddenly it got interrupted because the switch was opened, which means that there is a sudden LDI by dt kick or a sudden LDI by dt spike. There are many ways of seeing this. The inductor had stored energy previously. Now you already know that an inductor has no net energy consumption. If it stores some energy, it will have to release that energy back. Or in other words, if you try to interrupt the flow of current through an inductor, it will always disallow it by inducing an LDI by dt kick. Now it looks like that if say previously the current had been rising and it rose to say 10 ampere, and then suddenly you interrupted it and the current fell to 0 because it became an open circuit. So 0 minus 10, final value minus initial value, and this happened instantly. I mean, it took only the turn of time of the device sorry. So if the device turn off time maybe like of the order of 10 raised to the minus 6 1 microsecond, then a very high magnitude, if this goes, if you see, it becomes 10 raised to the 6 here, a very high magnitude L di by dt kick with a negative sign, 0 minus 10, a negative magnitude, a negative direction, high magnitude inductive kick is induced. So you see a voltage kick across the inductor like this. Now this inductor starts behaving like a source of energy. It has stored energy till now, and now it wants to release that energy. So it, just imagine something like a battery here, small battery here with a positive terminal in this direction, negative one in this direction, which will try to push current from its positive terminal. So it's momentarily behaving like a source of energy. It's not a battery, it's basically behaving like a current source. I just gave you the example of a battery to make it easier for you to understand. So now this inductor over here will ensure, through this voltage polarity induced across its terminals, it will ensure that current continues to flow in the same direction. But where does the current go? This inductor dumps some of its energy into the capacitor, some of its energy into the load, and then the return path, it forward biases the diode here, because the diode anode was here, this got forward biased, and the diode goes into conduction. So this energy that was stored in the inductor now freewheels in this path while storing some energy into the capacitor and some into the load. Again, it is not necessary that your capacitor might only be storing energy from the inductor. It could actually, the inductor and the capacitor could together be feeding the load if the load energy requirement is very high, or if it is low and the capacitor is also low in potential, this inductor might be giving energy to the capacitor as well as to the load. This will be clear to you when we do the waveforms, so please don't confuse yourself. What we know definitely is that during this interval, that is dTs to Ts, the inductor is definitely releasing energy. The capacitor, as we already discussed, might be releasing or might be storing energy depending upon the state of potential of the capacitor, state of energy of the load and the inductor. Now, during this interval, what is the voltage across the inductor? We will use the previous conventions. This was how we had defined the inductor voltage, the one in blue. So this is how we had defined it. Now this inductor voltage, and this is the load voltage we note. In the energy releasing interval, we have, let me use a blue pen. We have voltage across the inductor is equal to minus of V naught, which is negative, which means that L di by dt is negative, or you can say the current is now reducing or falling or decreasing, or you can also call it, you can say it in another term, that the inductor is now losing the energy that it had previously stored. Now if we just quickly do the volt second balance. Before we do the volt second balance, I want to also discuss the switch rating. What is the voltage across the switch over here? When the switch is conducting, obviously in the previous half cycle energy storing interval, it was obviously there was no voltage across the switch, maybe 2 or 3 volts, but let's just neglect it when we're talking in hundreds of volts. But when the device is off, the switch is supposed to block some voltage. And what is the voltage that the switch is blocking? It is the whole VDC coming across the switch. So voltage rating of the switch is VDC. That of the diode was minus VDC because it was supposed to block negative voltage, but this switch is supposed to block positive voltage, therefore its voltage rating is VDC. Now that's how you choose this device, a device that is fully controlled and a device that can block positive voltage has to be chosen here. So you either use an IGBT or you use a MOSFET, or any of the fully controlled voltage controlled devices. Now moving on to the volt second balance. So I would like you to note these few things. Voltage across the inductor in the first interval is VDC minus V0, which is positive. In the second interval, it is minus of V0, which is negative. Now, from inductor volt-second balance, we know that in steady state, in a complete switching cycle, that is from 0 to DTS and DTS to TS together, your inductor should not have stored, consumed, or given away any net energy. That means, now how does an inductor, I would like to explain something here. When an inductor stores energy, suppose this is the state of energy of an inductor. When an inductor stores energy, its current rises. It stores energy in the form of current, magnetic field. Its current rises, and when it releases energy, say this was DTS, and then there is a small interval TS. If this interval is small, this inductor should release energy fast, so that after the completion of this interval, IL reaches back to the same value and there is no net change in current. DI is 0. This is what it means that the inductor has released all the energy that it had previously stored. If it is not able to do that, what will happen? The inductor will burn out. Say it stores energy, then releases only some, then stores, then releases only some, then stores and releases only some of that energy. So basically that is an inductor going into saturation, or an inductor you can say going operating on a DC supply. But here you have an inductor operating on a switched DC supply, where you are ensuring that the inductor does not saturate by bringing it back to its its initial value of current, and you're ensuring that it does not just go on storing energy, but it also releases that energy effectively, so that it has no net consumption of energy. Now how do you signify this, how do you mathematically interpret it, is through the volt-second balance. You must have heard of the volt-second balance before. So what is the volt-second balance? The volt-second balance says that in a complete interval of switching, the net change in inductor current should be 0. That is, which signifies that the inductor has neither stored energy nor has neither consumed or given away energy. It has just stored and then released that energy. Okay. So now for an inductor, LdI by dt is equal to VL. And DI, if I want to integrate this DI, it will be VL dt upon L. Obviously L remains constant, so you can neglect it, which means that DI is equal to 0 is essentially volt-second is equal to 0. So integral of voltage across the inductor over the entire time period should be 0, which is the volt-second balance. And this is what signifies that an inductor has retained its basic property of neither consuming energy nor giving away any energy, stores and releases. So we are essentially putting that mathematically. Now from 0 to DTS, the voltage across the inductor was VDC minus V0, and the time interval was DTS minus 0, so you can call it DTS. And then later on in the second half interval, it was minus of V0, and the time interval was TS minus DTS, which is equal to 0. So you basically, in each interval, you find the voltage across the inductor, you product it with the time duration, and then you add all these intervals up together and equate this whole thing to 0. So if you solve for this, you get dVdc minus dV0 minus V0 plus dV0 is equal to 0. dV0 V0 is equal to d times VDC. Your classic buck converter equation. You must have already come across it in the previous semester, but as just repetition because I want to maintain the continuity. So V0 is equal to dVdc means that you are working with a buck converter. V0 is equal to d times VDC, where d is the ratio between on time of the device upon the total switching interval, which is T on plus T off, this TS, and it is obviously ranging between 0 to 1. So if you plot duty ratio with respect to, say, it goes from 0 to 1, this is your duty ratio, and you assume that the input of the converter is constant, then V naught will vary linearly as D varies, and at D is equal to 1, V naught becomes equal to VDC over here. So a linear curve, you have buck operation from 0 to VDC, you can smoothly vary your output voltage of the converter. So it's buck operation. If you see the reverse, we arrived at this equation V naught is equal to dVdC through the volt second balance. You can also say that volt second balance, I don't know how to put it in words. So volt second balance basically ensures that your converter behaves like, when the switches are arranged in the way that they are in a buck converter circuit, your volt second balance ensures, the inductor ensures that the output of the converter is equal to dVdC, and only in that case is the inductor balance maintained. So naturally it's the inductor dictating that it does not consume or give away any net energy, and that indirectly ensures that the output of the converter is D times VDC. When that happens, that's when your inductor has released all its excess of energy. Now we know about the volt second balance. If I want to tell you one more thing about the buck converter. So you have this buck converter and you have an input VDC and you have an output say V naught, and this V naught is a switching function of VDC. Switching is duty ratio. It is V naught is a function of VDC, and it also depends on obviously on VDC and on the switching action. Now V naught is a function of VDC, a switching function of VDC, and once this V naught is fixed, depending upon आपने ड्यूटी रेशियो क्या दिया है और आपका इनपुट क्या है, एक बार ये V naught फिक्स हो गया तो आपका जैसा भी लोड के अंदर रेजिस्टेंस कनेक्ट होगी, आपका एक I naught फिक्स हो जाएगा. ठीक, your I naught will be fixed, and then your IDC becomes a switching function of that I naught. Imagine it like a two-port network. You have a fixed input DC. The output is a switching function of this input DC, the output voltage. Once the output voltage is decided as a switching function of the input voltage, the output current becomes fixed because the load is fixed, the load resistance is fixed. And once the output current is fixed, the input current becomes a switching function of your output current. You can simply assume that it's a lossless converter. VDC IDC is equal to V naught I naught. Neglect the losses for now. You can directly find that IDC is equal to V naught upon VDC into I naught. So this becomes D times I naught. So IDC is a switching function of I naught. Okay, now coming back to your buck converter. So your buck converter has two very interesting components. Generally, not necessarily always, but usually you have them when your applications are those of power supplies where you want a regulated output. That is your L and C. So you have a load. लोड तो आपका यूज़र डिफाइन करेगा कि क्या लोड आपके कन्वर्टर पे पड़ेगा. इनपुट आपका ऑलरेडी डिसाइडेड है. डिवाइस आपने देखा है कि आपको एक रेटिंग का चूज़ करना है, एंड दैट रेटिंग इज़ इक्वल टू VDC. और डिवाइस जो दूसरा आपका डायोड है, दैट इज़ ऑल्सो चोजन टू बी एट अ रेटिंग ऑफ -VDC. सो यू हैव सेलेक्ट, यू कैन ईजिली सेलेक्ट योर VDC एंड यू कैन ईजिली सेलेक्ट योर डायोड. नाउ हाउ डू यू डिज़ाइन दिस L and C? Now let's go into the design of L and C. Let's start with L first. Now this L will basically determine the ripple in inductor current. इस करंट में कितना रिपल होगा ये आपका L डिसाइड करेगा, और जैसा रिपल इस करंट में होगा इवेंचुअली वैसा ही रिपल आपका रिफ्लेक्ट होगा इन द लोड ऑल्सो, एंड you would always want that smooth current flows through the inductor, and that will eventually ensure that you have a smooth load voltage profile also and a smooth load current also. So if you see the the equation determining an inductor, L di by dt is equal to VL, and you have, let's call it delta IL, the ripple in inductor current, which is di. You can say it is VL delta t by L. Now take any interval. You can say take the interval 0 to dts, where the inductor current was rising and it rose to its maximum ripple. Let's call that ripple as delta IL, peak to peak ripple, this peak to this peak. Let's call that delta IL. So this delta IL is equal to voltage across the inductor in that interval, and that interval was VDC minus V0 if we take the first interval. You can also take the second interval, doesn't matter. It is VDC minus V0. Delta T was DTS, and then you have L. So if we move further, you have delta IL. I can write V0 is equal to dVDC. It is VDC 1 minus D into D TS upon L. I can write it as delta IL is equal to dVDC को मैं V0 लिख सकती हूँ. So V0 1 minus D TS upon L, and V0 को I can write as I0 into R, and this I0 I can take it over here, and I know that these are average values. I know that the average value of load current is the same as the average value of inductor current, because the capacitor balance. Capacitor will when it's charging, it will take current. When it's discharging, it will give away current. But net current through a capacitor will be 0. Net change in voltage will be 0, and net current through the capacitor will be 0. So IL will be equal to the average IL will be equal to the average I0. Not the instantaneous values will not match, but their average values will match. So I can call it delta IL upon IL is equal to R into 1 minus D. TS को मैं नीचे लेके FS बना सकती हूँ, switching frequency, and L. So from this you can design your L, that your L is equal to R upon 1 minus D by Fs divided by fractional ripple, percentage ripple. आप अगर 5% ripple आपको बोला होगा, यानी कि 5% of average delta IL should be 5% of the average IL. So this is your equation for the design of L. Now what does this equation tell you? This equation tells you many things. It tells you that if you need a small ripple, you need to design a big L. Common sense. But obviously a big L means that it will occupy a lot of size on the PCB board. And if you want to reduce L, because that's ideally what is desired, and you want to reduce L even with a less ripple, then you can just increase the switching frequency. Higher the switching frequency, smaller will be the L for a given ripple. यानी कि अगर आपको 5% रिपल डिज़ायर्ड है और आपने 1000 हर्ट्ज पे इसको स्विच किया तो आपको बड़ा एल यूज़ होगा. लेकिन उसी 5% रिपल के लिए if you switch it at say 20 kilohertz instead of 1 kilohertz, if you switch it at 20 kilohertz, you will reduce the inductor size by 1 upon 20. This is essentially why you need power electronics. Because power electronics allows you to switch at very high frequencies, and that reduces or makes your size very, very compact. If you see, why is your why are your laptop chargers and all those chargers and everything, why is it so small? It is because of the ability of power electronics to be switched at, power electronic devices to be switched at very, very high switching frequencies, which indirectly reduce the size of your L and C. Your diodes and MOSFETs, they are already they are at very low sizes. Now when you reduce the size of L and C, that makes your system very compact. And especially अगर आप देखोगे तो सबसे ज़्यादा साइज़ आपके पावर इलेक्ट्रॉनिक सिस्टम्स में पैसिव्स का ही होता है, यानी कि आपके L and C's जो भी आपके कन्वर्टर में लगते हैं, पैसिव्स. And whenever you go at high switching frequencies, the size of these passives reduces. So like nowadays, a lot of research is going on wide band gap power devices like silicon carbide or gallium nitride. These devices are not made up of silicon, but obviously because of some doping in the form of SiC or GaN, gallium nitride, आप डिवाइस की स्विचिंग फ्रीक्वेंसी बहुत ज़्यादा बढ़ाते हो, उसके टर्न ऑन टर्न ऑफ टाइम्स बहुत रिड्यूस करते हो. And such devices can be switched even up to like megahertz range. And when you switch them at very, very high frequency, the advantage that you get is that your L and C are drastically reduced. It helps you in miniaturizing the circuit even more and more. So this is one of the most important aspects of power electronics, that you should know how high you can go. अब इतनी भी ज़्यादा switching frequency नहीं बढ़ानी है ना कि आप अपने डिवाइस को ही जला दो power loss create करके. You have to strike a very fine balance, that your switching frequency should be high enough that L and C are very small, but it should not be so low that it should not be so high that your device burns off, or it should not be so high that your device may not burn off, but you may need a very big heat sink to prevent the device from, but then the heat sink will increase the size. So it has to be a trade-off. You have to carefully select a switching frequency high enough for reducing the size of L and C, क्योंकि C का भी size depend, when you design C, you will see that the size of C also depends on the switching frequency. So generally it is desired in DC to DC converters that you operate them at very high switching frequencies to make them smaller circuits, and that's why we prefer generally MOSFETs over IGBTs, because MOSFETs have higher frequency of switching. Now let's design C. Actually we should have drawn the waveforms before designing these, but chalo koi baat nahi, now that we've started like this. Now the design of C will be based on the ripple that is in the capacitor voltage or in the output voltage. It will affect the ripple in the capacitor voltage or output voltage because they are connected in parallels. Now you know that C dV by dt is equal to IC, capacitor current. अब कोई भी इंटरवल अगर आप ले लोगे, आपकी कैपेसिटर करंट की इक्वेशन तो सेम ही रही, आई सी इज इक्वल टू आई एल माइनस आई नॉट. तो आप you don't want to use this equation. Let's try to manipulate it a bit. I can write C delta V is equal to delta Q, right? यानी कि किसी भी एक इंटरवल में आपके कैपेसिटर ने कितना अमाउंट ऑफ चार्ज स्टोर किया. ये इक्वेशन अब आप हम ऐसे रहने देते हैं, एंड लेट्स ट्राई टू ड्रॉ अ वेव फॉर्म. This equation I'll write here, C delta V is equal to delta Q. I know that my capacitor current IC is equal to IL minus I naught, whether it is 0 to DTS, whether it is DTS to TS. ये equation हमेशा, it always remains true because this node is always present in the circuit, right? So let me assume that my inductor current has some ripple, 0 to DTS it is increasing, then it is decreasing from DTS to TS. This is how my inductor current is looking like. And the output current is the average of this inductor current, say I naught. And I'm neglecting its ripple. इसको हम ripple free approximation भी कहते हैं DC to DC converters में, where you generally tend to neglect the ripple in the output current. ओके, टू सिंप्लीफाई थिंग्स, आपने ये अज्यूम किया है कि आउटपुट करंट में बिल्कुल रिपल नहीं है, और ऑब्वियसली इस आउटपुट करंट का एवरेज वैल्यू इज इक्वल टू द एवरेज ऑफ द इंडक्टर करंट. नाउ इफ आई वांट टू प्लॉट द कैपेसिटर करंट, it is IC is equal to IL minus I naught. So if I plot it, this is I naught. If I plot it, it is going to look like this. ठीक, this is your capacitor current and this is your DTS. Now see an interesting thing. From 0 to DTS, for some part the capacitor current is negative, which means that the capacitor is giving out current like this. It is discharging. And then for some part the capacitor is charging, which I had told you previously also कि 0 to DTS में आपका इंडक्टर कंटिन्यूसली एनर्जी स्टोर कर रहा है, लेकिन जो आपका कैपेसिटर है इट माइट बी ईदर स्टोरिंग एनर्जी और इट माइट बी रिलीजिंग एनर्जी डिपेंडिंग अपॉन द एनर्जी रिक्वायरमेंट ऑफ योर लोड एंड द एनर्जी स्टेट ऑफ योर कैपेसिटर, सॉरी ऑफ योर इंडक्टर. अब आपका जो इंडक्टर की एनर्जी जैसे 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 ज़्यादा होती जाएगी आपकी लोड की रिक्वायरमेंट से, ये देखो यहाँ पे आपकी इंडक्टर की एनर्जी IL इज़ ग्रेटर दैन द एनर्जी रिक्वायरमेंट ऑफ द लोड, सो ऑब्वियसली वेयर विल द एक्स्ट्रा एनर्जी गो, इट विल स्टोर एनर्जी इन द कैपेसिटर, सो द कैपेसिटर विल स्टोर एनर्जी. बट बिफोर दैट द इंडक्टर करंट वॉज लेसर दैन द लोड रिक्वायरमेंट, देयरफॉर द कैपेसिटर हैड टू डिस्चार्ज इन टू द लोड, इट हैड टू ऑगमेंट द इंडक्टर करंट. इंडक्टर भी एनर्जी दे रहा था, सोर्स से एनर्जी जो आ रही थी, इंडक्टर वो एनर्जी ले रहा था, और आपको लोड को फीड करने के लिए कैपेसिटर को भी कुछ एनर्जी देनी पड़ रही थी. सो दिस इज़ व्हाट आई मेंट व्हेन आई सेड इनिशियली दैट योर कैपेसिटर एनर्जी डिपेंड्स अपॉन द स्टेट ऑफ एनर्जी ऑफ द लोड एज वेल एज द कैपेसिटर. Sorry, inductor. So now if I redraw it, the capacitor is discharging, then it is charging, then it is charging again, then it is discharging. The capacitor current becomes negative, it means discharging, and when the capacitor current is positive, it means charging. तो इस केस में कैपेसिटर करंट के केस में देर इज़ नॉट अ यूनिफॉर्म पैटर्न कि 0 से DTS तक चार्ज ही हुआ है. यू सी देर इज़ 0 से DTS तक बीच में डिस्चार्ज हुआ, फिर चार्ज हुआ, नेक्स्ट इंटरवल में फिर चार्ज हुआ और डिस्चार्ज हुआ. बट इसमें भी आपने इंश्योर किया कि जितनी देर आपका कैपेसिटर चार्ज हुआ है उतनी ही देर आपका कैपेसिटर डिस्चार्ज भी हुआ हो. यानी कि अगर पूरा इंटरवल आपका TS है तो एटलीस्ट TS/2 टाइम तक, दिस विल बी TS/2 तक ये चार्ज हुआ होगा और रिमेनिंग TS/2 तक ये डिस्चार्ज हुआ होगा. ठीक है. नाउ व्हाट इज डेल्टा Q? इट इज़ द एरिया अंडर द कैपेसिटर करंट कर्व, राइट. नाउ दिस डेल्टा Q will be equal to half of base is TS/2 into altitude. What is this altitude now? Now this altitude, if you see, पीक टू पीक इंडक्टर करंट का रिपल कितना है? डेल्टा IL. और ये रिपल कितना हुआ? दिस इज पीक टू पीक. द सेम रिपल दैट वाज प्रेजेंट इन योर इंडक्टर करंट इज रिफ्लेक्टेड ऑन योर कैपेसिटर करंट, बट इट गोज इन द नेगेटिव डायरेक्शन. द सेम रिपल पीक टू पीक हेयर इज डेल्टा IL, बट यहाँ पे आपका इतना पोर्शन जो है विच इज गोइंग टू बी यूज इन द कैलकुलेशन ऑफ डेल्टा Q, दैट इज ओनली डेल्टा IL/2. So this is IS delta IL by 8. That is your delta Q, which is going to go in this equation. Now let's go back. You have C delta V is equal to half of base into altitude was delta IL by 2. Now let's design C. It becomes TS delta IL by 8 into delta V, right? ये इक्वेशन भी आपके लिए ठीक है, बट लाइक आई सेड जो आपका रिपल होता है दैट इज जनरली गिवन इन द फॉर्म ऑफ परसेंटेज. लाइक हमने जब L डिज़ाइन किया, वी डिज़ाइंड इट इन द फॉर्म ऑफ डेल्टा IL by IL, ताकि मैं आपको बता सकूँ 5% रिपल है विच इज़ दिस. Similarly, I would want this equation to be in the form of delta V upon V, delta V naught or delta VC, whatever you want to call it, load voltage, capacitor voltage upon delta V. इसलिए मैं इसको थोड़ा सा manipulate करूँगी. I know that L di by dt is equal to VL, and I know that delta IL is equal to VL dt upon L. मैं सेकेंड हाफ इंटरवल ले सकती हूँ, से आई कॉल इट वी नॉट होती है तब कैपेसिटर की इंडक्टर की वोल्टेज, और इंटरवल होता है 1 माइनस डी इंटू टी एस, और ये होता है आपका एल. ठीक, सो आई कैन से दैट डेल्टा आई एल इज इक्वल टू वी नॉट 1 माइनस डी टी एस बाई एल. नाउ लेट्स सब्स्टिट्यूट इट लाइक दिस. वी नॉट 1 माइनस डी टी एस बाई एल into 8 times delta V. Now let me simplify it a bit more. 1 minus d ts square into 8 into L into delta V naught upon V naught. Yani ki, now more interesting things. This is the design equation for C. This equation tells you if you want a less output load voltage ripple, less ripple in the output voltage, तो आपको C बढ़ाना पड़ेगा. ठीक, इसको अगर मैं नीचे लेकर आ जाऊं तो मैं सेम चीज़ रिपीट कर सकती हूँ कि अगर मैंने स्विचिंग फ्रीक्वेंसी ज़्यादा रखी तो सेम रिपल के लिए मुझे कैपेसिटर का साइज़ कम चाहिए. यानी कि 5% और 2% लोड वोल्टेज रिपल के लिए जो आपको 1000 हर्ट्ज़ पे कैपेसिटर चाहिए होगा, उससे बहुत छोटा कैपेसिटर आपको चाहिए होगा सेम रिपल परसेंटेज से, 2% रिपल, बट व्हेन यू आर ऑपरेटिंग एट 20 किलो हर्ट्ज़, अगेन द साइज ऑफ सी इज ड्रास्टिकली रिड्यूस्ड. एंड देर इज ऑल्सो अ रिलेशनशिप बिटवीन द साइज ऑफ एल एंड सी. इफ यू यूज अ बिगर एल, then you may have to use a smaller C. Do you get that? And if you use a smaller n, you will have to use a bigger C. There is also some relationship with duty ratio, even with L also. But what I'm trying to say is कि आप ऐसे नहीं समझना कि लोड वोल्टेज का रिपल सिर्फ कम होता है थ्रू कैपेसिटर. लोड वोल्टेज का जो रिपल है वो इंडक्टर से भी डिटर्मिन होता है. कैसे? अगर आप वेवफॉर्म देखोगे, अगर आपने बड़ा L यूज़ किया, if you use a big L, the ripple in inductor current will be less. When the ripple in inductor current is less, the ripple in capacitor current will be less, because the capacitor current is essentially with the same ripple, जो हमने बनाई भी, the same ripple as that of the inductor current. Now when the capacitor current has less ripple, और capacitor current के ripple से आपकी capacitor voltage की charging और discharging determine करेगी, तो obviously आपके capacitor voltage में कम, there will be less ripple, and that is your load voltage. So the ripple in load voltage is indirectly affected by L also and not just by C. Therefore अगर आपने पहले ही L को ज़्यादा रखा है, फिर आपको ज़्यादा C रखने की ज़रूरत नहीं पड़ेगी. You will have to reduce the size of C, or you can either use a bigger L. If you want to reduce the size of both, then use a very high switching frequency. So they're all interrelated, and the basic essence of this design is that that higher switching frequencies will always tend to reduce the size of your passives, and that will make your circuit very small. And that is why DC to DC converters use high switching frequency devices, especially MOSFETs, and nowadays silicon carbide MOSFETs, SiC MOSFETs, because they can be switched at very, very high frequencies. Now, before we end this lecture, I think it will be too long otherwise. I want to quickly draw some waveforms that we have, discussed already. It will not take much time. So, let's draw waveforms for buck converter. अभी तक तो हम continuous conduction mode में ही हैं. So, these are waveforms for continuous conduction mode. Let's assume that your voltage input VDC is constant. Obviously, it is constant. And you are switching it at some duty ratio, say DTS, TS, and repeat. Okay, this is your entire switching interval. Wait a second. Okay, so these are the pulses that you give between the gate and source of your gate and emitter, gate and emitter of your IGBT, or if you're working with MOSFET, then gate and source VGS. So these are the pulses that you give to your device. And if you see the inductor current is rising from 0 to dt as the inductor is storing energy and the inductor is releasing energy. It's storing and releasing. And if you see this is inductor current. If you see the inductor voltage, it is positive and equal to VDC minus V naught in the first interval, and then it is negative and it is minus of V naught in the other interval. So this is your inductor voltage VL. You assume that your load current is almost constant and average of the inductor voltage. Then your capacitor current IC will be IL minus I naught, and it will look something like this. The same ripple. So the capacitor may be charging and discharging within each cycle multiple times. Now this is your capacitor current, ये हमने पहले भी draw करी है. And from the capacitor current we can draw the load voltage or the capacitor voltage. We see the capacitor is discharging, so this voltage is falling till here. The capacitor is charging, so it is rising. It is discharging, so it is falling and rising. This is generally assumed to be flat. With you neglect this ripple, your capacitor is assumed to be big enough so that this ripple is flat, and because V naught becomes flat, it's assumed to be flat, therefore you assume I naught to be flat, which I told you it's the ripple free approximation. But you should know that the design of L will determine the ripple in inductor current, which is in turn the same ripple as that in the capacitor current, and the ripple in this current will in turn dictate the ripple in the load voltage, and which means that the inductor as well as the capacitor determine your load voltage ripple. It's a misnomer. Many people feel and many people believe that the capacitor voltage, the capacitor is the only element that determines the ripple in load voltage, but it is wrong. The inductor and capacitor together determine the ripple in the load voltage. The inductor also has a role to play there. In fact, this was one of the questions I was asked in my interview at IIT, and that is it just the capacitor, or does the inductor also determine the ripple, output voltage ripple? Then we also have the diode in the first interval 0 to DTS. The diode is blocking minus VDC, and then DTS to TS it is conducting, so almost zero voltage. And if we draw the voltage across the switch, 0 to DTS it is conducting, so it is 0, and DTS to TS it is blocking plus VDC. So this is your waveform across the switch. So that is all for waveforms, but till now we have only assumed that our inductor current is continuous. We are operating in CCM. In the next lecture we'll move on to DCM. So we may also have a doubt clearing session later in the week. Please let me know your feedback in the WhatsApp group and try to be regularly following these lectures, because bioelectronics is a subject that if it goes right once, it goes right forever, and if it goes wrong with you once, you probably never overcome that weakness. So make sure that you understand it well and you put in enough effort to know the subject. Wishing you the best of luck, and keep me posted.